Hey everyone, welcome to this lecture for P80-105, a course on data science. This is the last in a collection of 3 videos on linear models, a really useful framework for doing data analysis. And in particular, in this video, we're going to be talking about bootstrapping as a way to do inference in non-standard settings. I'm going to start by giving an introduction using slides, and after that, I'll demonstrate the material in a screencast. Feel free to skip around to the parts of the video you find most useful. To get the most out of this, I do encourage you to code along with me. Everything is available at p80105.com. There are links below. Fantastic. Let's get started. Cool. I'm going to start by talking about why we might do some bootstrapping. And to do that, I'm going to revisit a slide that we saw in a video for simulation, and that's to talk about repeated sampling. As we said then, repeated sampling is the conceptual framework that really underlies a lot of the tools that people use in statistics. Again, the idea behind repeated sampling is that if you want to know something about the population mean, well, what you're going to do is go out into the population and you're going to draw a sample and you're going to compute a sample mean. And the idea for repeated sampling is that if you understand what would happen if you did that process over and over and over, if you know, I go to my sample, I compute a mean, I go to a sample, I compute a mean, I go to a sample, I compute a mean. Under repeated sampling, you can say something about the distribution of the mean in your sample, the distribution of your sample mean, and use that information to come up with some plausible idea about what's actually going on in the population. Right? You can use your sample mean and the distribution of your sample mean to construct things like confidence intervals, and for hypothesis tests, compute p-values and do things like this. And it's all sort of based on this idea of what happens if you go to the population and you draw a sample and you compute something. You do something in your sample, right? And of course, that doesn't actually happen in reality. What happens in reality is you get one sample from your population and you compute one thing, and then you trust that whatever sort of statistical arguments you've made under repeated sampling gives you some way of making a claim about what's going on out in the population based on just the one sample that you have in front of you. In simulations, or we talked about simulations as a way to mimic repeated sampling, as a way to sort of clarify what happens, right? Like if you really did go out into a population that you're making up, if you can control that population, you can then generate data under whatever mechanism you want, you can do the analysis that you care about, you can understand what's going on for a particular thing in a particular setting. Sometimes that's to confirm that statistics really works, and sometimes it's to say, like, this is a non-standard object, this is something I don't really understand what's going on and I want to simulate to see what's happening. And just like we said then, repeated sampling can happen on a computer. Now, we're not just going to be doing simulation again. What we're talking about now is bootstrapping. And like simulation and like cross-validation, bootstrapping is one of these iterative approaches. It's something that you do over and over and over and over. You do the same thing over and over and over. And it is really difficult to overstate how critical this is in modern statistics. It's just one of the sort of foundational tools now that people have relied on more and more in the last several years. So the basic idea is, again, like, you're not actually going to get to go out into the world and do repeated sampling, but sometimes it'd be nice if you could act like that's something that you were going to do. So instead of generating or going out into a population and gathering new data, you just sort of use the data that you have and treat that as a population, and then you start drawing samples from that. So what you'd sort of like to do is be going over here into the universe and drawing, like, from your population, draw a sample, go back and draw a sample, go back and draw a sample. And you can't actually do that. So what you do is you go out and you draw one sample, and then you say, like, all right, well, this should be kind of what my population looks like. So I'm just going to start here and draw a sample, and start here and draw a sample and draw a sample. Now, given that you only have that one data set, what you're trying to do is sort of mimic the process of getting repeated samples. So you start here and you draw a sample of the same size, but with replacement. So this with replacement idea is that you might be sort of hanging out over here, and you're going to take a person and you're going to put them in your little Bootstrap sample bucket, and then they go back into your sample. So you might draw that person twice in a Bootstrap sample. You might draw a person 0 times in a Bootstrap sample. Fine, whatever. If you do that, if you sort of draw from your sample with replacement, that process, it turns out, mimics the idea that you're sort of going back to your original population and drawing a sample, right? That sort of, it seems like a strange leap, but if you're sort of thinking of your sample as representative of the population, well, if you draw a sample from your sample, that's also sort of representative of your population. And if you draw that sample with replacement, you get some variability from one Bootstrap sample to the next. And that variability, again, should mimic the kind of thing that would happen if you were really doing repeated sampling. So I've sort of said this is what you're going to do for one bootstrap sample. You have your sample, you take a person, you put them in a bucket, and then maybe they go back in, maybe you draw them again, maybe not, and you have a bootstrap sample. And then you analyze that data set. It's the same size as your sample, but it's sort of different because some people are drawn twice, some people are drawn 0 times. You analyze your bootstrap sample using whatever method it is you're interested in, and then you just do that again, right? You get a new bootstrap sample and you analyze that again, and you get a new bootstrap sample and you analyze it, and another one and another one and another one. And so this process really does mimic the idea of repeated sampling. It gives you some idea of saying like, all right, across 100 or 1,000 bootstrap samples, what is the distribution of the mean? What is actually the distribution of the sample mean across 100 or 1,000 bootstrap samples, right? And that process is sort of trying to do the same thing as you would do if you could do repeated sampling, but you can't. So you're using a computer to take care of this for you. And you might be thinking to yourself like, well, this sounds extremely complicated and maybe time consuming, and I'm not sure why I want to do it. Well, it turns out to be useful because repeated sampling works in certain settings, right? Repeated sampling frameworks gives you theoretical results under a variety of assumptions and sometimes also asymptotic limits. And what I mean by that is you might have to start out and say, well, this is the distribution of the sample mean as long as my data aren't too skewed, or as long as my data follows some sort of a distribution like this. Or you might say, you know, the distribution doesn't matter. This is the distribution of my data doesn't matter. The sample mean follows this distribution as long as n is large enough. As long as I have enough people, well, then everything sort of becomes a normal distribution, right? Regression coefficients follow a normal distribution. Odds ratios, log odds ratios follow normal distributions, right? Like things sort of follow normal distributions as long as you're in a setting where either the data are reasonably well behaved or you have large sample sizes. Sample sizes going to infinity is what we talk about with asymptotics. So that's great, and you can do the things that you need to do in those settings. But if your assumptions aren't met, or if your sample size isn't large enough, you can't just sort of say, I know that this follows a normal distribution. You have to do something else. And if the theoretical results for repeated sampling don't work out, bootstrapping gives you a way to say, well, let me just check. I don't know what distribution this follows. I don't know what this is supposed to look like. So I'll just repeated sample a whole bunch of times and everything's going to be awesome. And then given that, I can just sort of check what is the distribution of the parameter that I'm interested in repeated sampling across all of these bootstrap distributions, and use that to get an idea about the upper and lower limits. Use that to get an idea about like a confidence interval for the parameter that you're interested in the same framework as you would if you were sort of trusting theoretical results. So you can code this up. Coding up the bootstrap turns out to be a really natural application of some of the iterative tools that we talked about in a previous collection of videos and that we relied on when we were doing cross-validation as well. So the idea is to either write a function or use a function that draws a sample with replacement. So you got your bootstrap sample here, and then you analyze that and then return whatever object describes the analysis that you're interested in. And then you do that a bunch of times. And so if you can do that iterative thing, especially in a way that allows you to keep track of the bootstrap samples, the analysis that you're interested in, and the results that you're interested in. If you can keep track of all of that in a single data frame, well, that's even better. And it turns out, of course, we're not going to make it through this without talking about list columns. That's exactly what you want to do if you're doing a bootstrap, is have a list of bootstrap samples, and then analyses, and then results, and then you summarize some things. And boy, that's just super exciting for me. I'm thrilled about doing both the bootstrap and list columns. And so with that, let's go ahead and jump into it. Fantastic. I'm going to jump in and start writing some code to do the bootstrap. I've got the usual framework here. I've got an R Markdown document. I'm loading tidyverse, and we're going to see modelr a little bit later on, and I'm making some stuff ready for plots. We're going to start out by looking at a couple of simulated data sets, and then we'll revisit a real data set in a couple of minutes. And I'm going to sort of start out by talking about how we're simulating the data. We're going to be using the Bootstrap to look at simple linear regression. And the first example that I have here is generated so that I get X following this distribution, and then I get errors are sampled from a normal distribution, and then Y is 2 plus 3 times X plus the error. And then I've got a second data frame that starts out in the same way as the first, so it's got the same X values, exactly the same X values, and then it takes the error terms and multiplies those by 0.75 times X, and then generates Y in the same way, 2 plus 3 times X, plus this new error structure. And you might sort of wonder, like, why is it we're going to be looking at these two things? So I'm gonna plot these real quick, plot the data sets. So I'm going to start with simdf constant, and let's do ggplot X on the X-axis and Y on the Y-axis. And let's do geom point, and then I'm going to do geom smooth with method equal lm. And the reason here is to sort of show the best fit linear regression line on top of this data set. So what I get here is X on the X-axis, Y here, and if you sort of look, there's a linear association, and the residuals, the error terms are, sorry, the observations are evenly scattered around this best fit line. The residuals here have constant variance over the entire X-axis. And so in that sense, this is a data set that goes along very well with most of the assumptions that you usually encode in a simple linear regression, right? If you take a step back and you ask what's going on with a simple linear regression, very often you assume, well, you need to have like no patterns that you're missing. You need to have a line that actually works, and you need to have residuals that have constant variance, and there are some other assumptions also. And so this works. This matches all of those assumptions. The other data set doesn't, and that's where things get a little bit interesting. So here, simdf non-constant. Let's try again. Okay, so here, when X is close to 0, the residuals are really, really small. And that makes sense because in this data set, I am taking whatever error term I had previously and multiplying it by X. So when X is close to 0, I get almost no residual variance. And then on the other hand, when X is sort of far from 0, the residuals spread out quite a bit. And so in this data set, you can do simple linear regression. You can fit your regression line. But one of the key assumptions, especially the key assumption that shows up when you start trying to do inference, when you start trying to construct confidence intervals for your regression coefficients, one of those assumptions is just fundamentally wrong. And so the the usual kinds of inference that you might do is just going to be incorrect. The assumptions that you make to do inference don't match the data that's actually in front of you. And so the methods that you would use to build a confidence interval just sort of don't work here. And that's going to be the problem that we, in this case, are going to try to solve with a bootstrap. I guess I want to be clear. You can still, in a data set like this, you can fit ordinary least squares. That works fine. You can get your estimate for the intercept and the slope, and that works fine. The problem comes from trying to guess how much uncertainty there is in those estimates, right? How wide should your confidence interval be when you start looking at those estimates? And that's the thing that we're going to spend a little bit of time working on right now. I guess before I do that, I'm going to take one other step. I'm just going to sort of fit linear regressions to both of these. So let me do lm of y against x when my data is simdf constant, and take a look at that. Oh, that's awful. Room tidy that. Okay. And then I'm going to do a similar thing with simdf non-constant. And sort of what I want to point out here is the estimates are pretty similar to each other, which is not surprising. They're both relatively close to 2 and 3 for the intercept and slope, respectively. But what is a little bit surprising is that the standard errors that go along with the intercept and slope are also pretty similar. They're about 0.1 for the intercept and about 0.07 for the slope. And the reason that I say that that's interesting is if I sort of compare my two data sets, in this instance, there's quite a bit of variability right here around 0, and then relative to, the same amount of variability sort of out here in the tails. And so if I'm thinking about what I really don't know in this, I think like I probably don't have a great, maybe I don't have a great estimate of the intercept, but as things sort of spread out, it's still doing fine. Like out in the tails, when I get over to x equals 2 or 3, I know pretty well where this line is supposed to be. On the other hand, here, when I get out to 2 or 3 in this data set, there's a lot of places where this line could plausibly be. There's quite a bit of uncertainty in that slope, but over here at the intercept, there's almost no uncertainty. I should have a really good idea of where this intercept is going to be. And so what I would imagine is in this data set compared to this data set, I should have here more uncertainty in the slope and less uncertainty in the intercept. And I don't have that at all. I've got same amount of uncertainty in intercept and slope comparing these two data sets. If I sort of build this linear regression model and get confidence intervals, I get estimates and standard errors that are based on the usual assumptions that you would make if you were doing linear regression. And again, LM is sort of giving me those results as if those assumptions are true. It doesn't know better, it's just spitting things out. So that's again the problem that we want to solve here. So the way we're going to solve that is using the bootstrap, right? So again, what the bootstrap is going to try to do is say, what if I know the assumptions aren't met in this data set. I know the usual assumptions that I would need to construct a confidence interval are not met in this data set, and there are other ways that you could solve this. If you wanted to do like a weighted least squares or generalized least squares, you could probably do something like that here, but that sort of opens its own can of worms. In this case, what we're going to do is say our assumptions aren't met, so I need to understand what the distribution of my intercept and slope are going to be under repeated sampling, and I'm going to get that distribution using the bootstrap. Right? Again, I can get estimates of the ordinary least squares, I can run ordinary least squares. I can get estimates of the intercept and slope for this data set. The estimates I'm fine with. The problem is I don't really trust the confidence intervals. I don't really trust the uncertainty estimates that go along with those things. And that's what we're going to try to get under repeated sampling using the bootstrap, is to say, what if I had another data set that looked like this one, and I got an intercept and slope? And then I got another data set that looked like this one, and I got the intercept and slope, and another, and another, and another. And could I, from that collection of repeated samples and the collection of intercepts and slope that go along with each of those samples, could I just look and see, well, okay, what is the actual variance of the intercept estimate? What is the actual variance of the slope estimate under repeated sampling? That's what we're going to do with the bootstrap. Okay, so draw one bootstrap sample. Okay, so what I'm actually going to write a function that draws a bootstrap sample, and the reason that I'm writing the function is so that later on I can rerun that function a bunch of times, right? So what I'm going to do is write a bootstrap sample is a function of a data frame oh, I'm like looking at this, I'm like, why isn't it making that a different color? It's because none of this is inside of a code chunk. Oh, that's, you never realize how dependent you are on seeing something in blue until it's not blue. All right, so I'm writing a function that's going to generate a bootstrap sample based on a data frame. And this function is actually going to be pretty simple. I'm going to take advantage of a tool called sample frac. And what sample frac does is it draws a sample of a particular proportion of your data set, and I just want that proportion to be 1. So I'm going to draw a sample from the data frame that I'm passing in as an argument, and it's going to by default draw a sample that is the same size as the data frame, and then I'm going to set, instead of replace equals false, this is the key thing, instead of replace equals false, I'm going to set replace equals true. Now, there are a couple of questions you might ask here. I guess sort of the first is, why do you want it to be the same size? It's because confidence intervals or variance estimates are really dependent on the sample size. If you have a lot of data points, you're going to get tighter confidence intervals. If you have fewer data points, you're going to get wider confidence intervals. And so here, when I'm drawing a sample, when I want to mimic the uncertainty that I have in this data set, I want to keep that sample size fixed. And again, I'm drawing this sample with replacement so that I don't get exactly the same data set that I started out with. I might get this observation twice in one bootstrap sample, and I might get it 0 times in a different bootstrap sample. And that's fine. That's going to mimic the kind of uncertainty that I would get if I were really going back to a population and generating new data sets. So, all right, so sort of back to my function here. If I plug in I plug in any data set. I'm going to draw a sample with replacement of that, draw a sample with replacement from that data frame. And I'm actually going to do one other thing here. I know in this case, I know that the data frame that I'm going to pass in has an X value and a Y value. And so I'm going to put things in order. I'm going to arrange the result of this according to X. And that's going to make it easier for me in just a minute to like look at what's going on here. This is not a critical step. Arranging your data doesn't change any of your results. This is just to sort of clarify things in just a second. So let me define that function and then check how it works. So check if this works. So what I'm going to do here is take my sim df non-constant and I'm going to do a boot sample of sim df non-constant. Okay, so what I've got, I've passed this data frame into my bootstrap function. It has drawn a sample with replacement of exactly the same size, and now I want to see if this works. So when I run the boot sample function on this, what I get is a data frame of size 250. That looks to be about right. And I'm getting some observations twice. I get this one twice. I get this one 3 times. I get this one twice. And although I'm not sort of looking at the full data set, if I've got this one twice, then there are going to be some rows that I don't have at all. If I've got this one 3 times, there are going to be some rows that I don't have at all. And so let me just sort of run this again and see. Now I get a different bootstrap sample, right? So if I run this again, I get a different sample drawn with replacement from my data set, but it's got size 250 and 250 again and 250, right? So it looks like this function is working about the way that I want it to. And let me just sort of do one other thing. That's a data frame, so I can plot this. Let me just copy from here. And I'm going to do g on point with alpha equals 0.3 and check. So the reason I set alpha equals 0.3 is so that you can tell here, like some of these points are a little bit lighter. This point is a little bit darker because there are 2 or 3 versions of this observation in my data set. And if I run this again, I get a slightly different data. And if I run it again, I get slightly different data. And I'm getting different regression lines each time also. It's a little bit hard to tell. Maybe I'll try one other thing to drive this point home. If I do y lim, let's say -6 to 16, -5 to 16, and I run this a couple of times, you'll see I get different data sets each time. I get different data sets each time. My line sort of, it's not moving a lot. I don't have a huge amount of uncertainty, but my line moves a little bit also, right? It sort of shifts back and forth, up and down. Okay, so great. This is sort of what bootstrapping is supposed to do. I'm generating a bootstrap sample, and here my analysis is just like look at the plot. But what we're going to try to do is say, can I actually estimate that intercept and slope and save those across bootstrap samples? And the answer is like, yeah, of course I can do that, right? So if I wanted here, instead of doing this plot, I could fit, lm y against x using whatever data set has just come out of my bootstrap sample, and let's do room tidy on the result. So here I get an estimate 1.87 and 3.2. If I run it again, 1.9, 3.19, 3.1, 3.1, right? Great. All right, so this is the kind of thing that we now, again, instead of, I guess I'm like doing bootstrapping in real time right now. I'm just drawing samples with replacement and then analyzing it using linear regression. And that's great, but that's not really a real cohesive way of doing this analysis. So now what I'm going to try to do, I haven't knitted or committed in a minute, so I'm going to do that first. What have we done? Simulate data, draw bootstrap samples. Okay. All right, so what I really want to do is mini samples and analysis. Okay. So when I say I want to draw mini samples, what I'd really like to have is just 100 or maybe 1,000, let's go for 1,000 bootstrap samples drawn with replacement from this data frame, right? I just want a whole big long list, and each one of them should be a slightly different sample drawn with replacement from the sample that I already have. I want that to sort of be the thing that I'm keeping track of. And so I wrote this function a minute ago so that I can do something like the following, right? So my goal here is going to be to do a bootstraps data frame, and what I'm going to get is a tibble where I'll say, I want the strap number is going to be 1 to 1,000, and then the strap sample is going to be rerun boot sample here, and I'm going to rerun that 1,000 times. I guess sort of the order here is maybe the other. So I got to tell it how many times to rerun and then what to rerun. And if I run these lines of code, it takes a minute because I'm drawing a bunch of Bootstrap samples. It doesn't take that long. Okay, so let me just sort of double check the head of my tibble. Right? So I've got 1,000 rows, which is great because I've told it I want to do this 1,000 times here and here. And I've got the bootstrap number 1, 2, 3, 4, 5. And this strap sample is going to be a data frame, and then a data frame, and then a data frame, and then a data frame, right? And we can sort of double check that this is doing what it's supposed to. If I do bootstraps, and let's pull strap sample, and I'm going to look at the first element here is a data frame. Then if I look at the second element, I get a different data frame, and the third element is a different data frame. Right? So it's doing the things that I want to do. And what's great about this is once we've gotten to this point, we've got like a data frame. I mean, we're sort of right back at a place where we can use the same iterative analysis techniques that we've used in a couple of other places. We can do the same thing that we did when we were analyzing nested data across boroughs in Manhattan, and across neighborhoods in Manhattan, or if we're doing cross-validation, we've got like a list of data frames and we need to do some analysis on each of those. Now all we have to do is like the same kind of a thing. So can I run my analysis on these? And the answer is going to be yes, using exactly the same kind of thing that we did before. So if I started to work on this, what I'm going to do is take, say, bootstrap. I'll do boot results. I'm going to say this is a new thing. So I got my bootstraps, and what I want to do is fit a regression to each data frame, and then given that regression, get the results. And then given those results, to do something with those. And we'll sort of talk about what that something is in just a second. So if I want to fit the regressions and get the results, that's sort of step one. I'm going to use my mutate and map combination. So I want the models to map across strap sample. And I want to fit a regression y against x, where data is whatever element dot x, I'll be clear here, dot x is strap sample, and whatever strap sample I'm interested in, I'm going to get a regression for that. So I'll get a linear regression for the first one, and for the second one, and for the third one. Okay, let me just, that's gonna take a minute. Is it gonna take? No, it's actually really quick. So that's great. Like at the very least, this code works. I haven't done anything to double check that these models are in fact different from each other. But for now, I'm just going to sort of trust that writing the same code that I've written before is going to be about the same, and we'll look at these results in just a second. So the next thing that I'm going to get is my collection of results, where I'm going to map across models and just run broom tidy on each of those. You see, does this work? Yes. Let's check. Yep. So now I've done, for each bootstrap sample, fit a linear model and extracted using broom tidy the intercept, slope, estimates, p-values, whatever other things. Okay. And so given all of this, I can do the usual kinds of next steps. I'm going to select only strap number and results, and then I'm going to unnest the results column, and this is really going to be all of my results. All right, so what do I have now? So let me just start out and look at the Bootstrap results. Okay, so this is a long data frame, 2,000 rows, and it's 2,000 rows for the following reason. I have 1,000 data sets, and for each of those data sets, I fit a simple linear regression and gotten an intercept estimate and a slope estimate. All right, so I've got intercept and slope for data set 1, intercept slope for data set 2, up to intercept and slope for data set 1,000. And that's pretty great. Now, again, I guess I want to be clear. I don't really care in this about the standard error, the statistic, or the p-value, right? For each data set, the standard error, statistic, and p-value are computed under the usual assumptions of doing ordinary least squares, or under the usual assumptions for regression. And I know that for this data set, it doesn't actually work that way, right? Like that's not really the thing that it's supposed to be. So really what I'm interested in here is the distribution of the estimated intercept and the estimated slope under this sort of repeated sampling framework. My hope is that this estimated intercept and estimated slope are going to sort of, under this repeated sampling framework that I'm mimicking doing a bootstrap, that the variances of those things are going to be closer to the actual variance than what I get if I make the incorrect assumption and just sort of compute a standard error here and here. So that's what I want to take a look at next is what does the distribution of that estimated intercept and slope actually look like, right? So the standard error is supposed to be something like a standard deviation of this estimate under repeated sampling. And we've computed that above, and now I'm just sort of want to see in the Bootstrap samples, what is the actual standard deviation of my estimates under repeated sampling, okay? So how am I going to do that? Well, I'm going to take my boot results, and I'm going to group by the term that I'm interested in, and I'm going to summarize so that my mean estimate is the mean of the estimate, and the standard deviation of my estimate is the standard deviation of the estimate. Okay, let's run this and include the last parentheses. A term not found. Oh, that's weird. Okay. Okay, so what have I done here? Now, again, the process for the Bootstrap was to mimic repeated sampling, was to take a sample from the data set, to take one sample from the population and then redraw samples from that sample and get an idea about the uncertainty in the intercept and the slope across Bootstrap samples. And in that way to sort of say, what is the actual uncertainty in my intercept and the actual uncertainty in my slope across the actual repeated sampling process, right? So here, I'm using the Bootstrap as a way to say, I know that linear regression is going to assume constant variance, and I know that constant variance isn't the right assumption. So whatever the usual linear regression stuff says about the variability in my intercept and slope, well, that's just not true here, right? I just know that that's not going to be what I need to have. And so the Bootstrap has given me a way to get the actual standard error under repeated sampling, not assuming constant variance. I'm not making any assumption about the residuals when I'm doing the Bootstrap. I'm just saying, like, well, what if I did the same thing over and over and over? What if I just drew samples from my population over and over and over? Can I mimic that? And without making an assumption about constant variance at all, can I get some idea about what the uncertainty in my estimated intercept and the uncertainty in my estimated slope, what are those quantities supposed to be? Now, I want to compare this to what we had done previously. And what we did previously was use linear model and sort of knew in the back of our minds that this was going to assume constant residual variance. And the fact that the intercept went from 0.7 to 0.1 standard error, and this went from 0.1 to 0.7, that's sort of a coincidence rather than anything that just sort of happens. What I want to be clear about, though, is that if you compare the Bootstrap estimate of uncertainty, the Bootstrap standard deviation of my intercept, this standard deviation is lower than it is if I assume constant variance, if I just use the off-the-shelf linear model stuff. And meanwhile, if I look at the Bootstrap uncertainty in my slope, it's higher, it's about 0.1 rather than 0.07. It's higher under the bootstrap than it is if I assume constant variance. And if I go back to the plot that we made previously, that sort of makes sense, right? In this data set, and this I guess is one of the bootstrap samples from this data set, but that's fine. In this data set, when we sort of looked at it, we said, you know, I should probably do better at estimating the intercept here and worse at estimating this slope because there's sort of wide range of stuff going on here. I should do better at the intercept and worse at the slope than I would do if I was sort of assuming constant variance, right? And that's exactly what happens. So that's, you know, I'm sort of waving my hands a little bit, but I'm saying looking at this data set, it seems like the bootstrap is doing the right thing. It seems like it's sort of getting uncertainty estimates here and here that are a little bit more reflective of what actually happens in this data set. And so that I think is just pretty exciting. I can do other things here. So I guess like the thing that you could do if you wanted to with this is to say, given an estimate and a standard error, can I do something like constructing a confidence interval, or even better than that? If you're thinking about, you know, you want to construct a confidence interval, you could say, well, I want to have a confidence interval where 2.5% of things is left out at the lower tail and 2.5% of things is left out at the upper tail. So let's sort of take a look first at distributions and then at how you might construct a confidence interval. So look at the distributions. And what I mean by that is I'm going to say, what do I want to do? I'm going to say, let's take my bootstrap results and I'm going to make a plot. And on the x-axis, I want the estimate, and I'm going to do geom density, and I want separate ones of these. I'm going to do facet wrap against term. And this is, I mean, it's a little bit strange because I'm like getting estimates over this entire range here. Is there a way that I can do that? I'm actually, let's just sort of worry only about the intercept for now. So let me get rid of this. Sorry, let's worry only about the slope. I'm going to filter term is x, and then take a look. So this is, again, under repeated sampling. I can't stress enough how great this is. What we're doing here is saying that under repeated sampling, this is what the actual distribution of estimated slopes is going to be. That I'm not sort of relying on ordinary least squares. I'm not relying on linear model theory to give me some idea about what the standard error is. I'm using the bootstrap to say, this is the kind of uncertainty that you would get in this data set, in data that looks like this, if you did repeated sampling. Now, if I wanted to construct a confidence interval, I might want to go here and sort of chop off, 2.5% of observations here and chop off 2.5% of observations there. And so that's the kind of thing that we're going to try to do next. So construct bootstrap confidence interval. And the way that I'm going to construct my bootstrap confidence interval is getting my bootstrap results. And I'm going to go ahead and group by term again. And I want to get a few things. I'm going to summarize. Let's do CI lower bound is going to be the quantile of my estimate, and I want the 0.25 quantile. 0.025 quantile should be my lower bound. I'm sort of hoping that this works. And then I want the upper quantile, I want to chop off everything that's 2.5% that way. So I'm going to start at 0 and go to 97.25. So I want, 97.5. And that should be my confidence interval. Let's double check. Oh, sorry, this should be upper. So here what I get is a confidence interval based on repeated sampling, just sort of saying, listen, I drew 1,000 samples and I'm sort of cutting things off at 2.5% and 97.5%. And that gives me about 2.91 here and about 3.31 here, right? So that's going to be my bootstrap confidence interval. That's going to be the thing that I'm interested in. And that's just, man, that's just really great. I'm really excited about this. So that's the kind of analysis that you might do with the bootstrap. I'm going to do a couple of things very quickly. The first thing that I'm going to do is bootstrap using modelr. the modelr package instead. So we're using the modelr package when we were doing cross-validation to automate as much as possible this process of drawing repeated samples and then analyzing those. So can we simplify anything? Simplify anything. The answer is going to be yes. So if I start out with my sim data frame non-constant, and then in the modelr package, there's a handy function called Bootstrap that says, give me a data set and tell me how many Bootstrap samples you want. And I'm going to say I want 1,000 Bootstrap samples. What this is going to do is create that same sort of a structure that we did by hand when we were talking about that we did by hand when we wrote a function that said draw a sample with replacement, draw a sample with replacement, draw a sample with replacement. That's sort of what we've got here. And sort of like with cross-validation, the modelr package is creating a resample object, not a data frame. And the resample object is a little bit more, it saves memory. It's not storing that data frame over and over and over again. It's just sort of storing row numbers. In cross-validation, in that video lecture, we converted all of these resample objects to data frames, and that was so that we could use the MGCV package. The MGCV package does not play well with resample objects, but something like fitting a linear model actually does. That works just fine. So what I'm going to say we can do is the same kind of thing that we have already done. So I'm going to copy and paste all of this and see what happens. So now the thing that I want to iterate over is not, I called it strap sample above. Now I want to iterate over the column called strap, and then select, I'm going to say, rename this .id column if I can. Actually, I'm going to do that a little bit differently. I think here you can say in the Bootstrap thing, ID, it's the column name that you want to have. So I'm going to say I want my ID column to be strap number, right? So all I'm doing is replacing this .id with a column named strap number, and then I can sort of save that result here. So this is simdf non-constant. Let me just sort of run all of that. That's going to take a minute, and that spit out a bunch of results. And now let me, same thing here, group by term, summarize and get my mean and standard deviation. Takes a second. And these are about the same, right? So in this instance, I think previously this had been like 0.074 and this was 0.1 something, 102. So these estimates are a little bit different, right? Because I'm drawing 1,000 Bootstrap samples and I'm not going to get the same 1,000 Bootstrap samples every single time. So these are in the right ballpark. They're in the same ballpark each time I do this 1,000 times. They're a little bit different. If you were, if you were really concerned about getting this exactly right, you might do 5,000 or 10,000 or something like that. For now, this works. If you were writing a paper based on this, you would probably want to crank up the number of iterations a little bit more. But this works, right? And so, gosh, I'm looking at this, and this is what, 12 lines of code. And what we're getting out of this is from this data set starting point, we're generating 1,000 Bootstrap samples, analyzing and summarizing each of those, extracting the results, and then summarizing those results to get my mean and standard error of the estimates. This is, this is mind-boggling, both that this is a thing that we are able to do, and that it's actually, there's a lot of this code that is not super complicated, right? At least from this point on, we're just sort of taking some results and analyzing them using usual tidyverse kinds of things. And even this takes a while to get used to. No joke, it takes a while to get used to doing this kind of a thing. But I think it's exceptionally powerful to be able to do this kind of an analysis in a way that's this quick. I guess another thing that I want to point out, just as like a check on sanity, can we use this same code to analyze the constant residual variance setting, right? So again, I guess what I've been saying all the way through here is that the Bootstrap works pretty well if your assumptions are not met. But what if your assumptions are met? Does the Bootstrap still sort of work? This is like a useful logical check. Does this do something that seems reasonable? So here again, it's sort of drawing all of those samples, and I just want to remind us of what we had seen previously when we fit that linear model using that data set. So here, the Bootstrap is giving me an estimate of 0.198 and those are about the same, and the standard errors are pretty similar also. It's a little bit higher here than it is here. That might be, the fact that I've done this 1,000 times instead of 5,000 times, and it might be that there's just a little bit of some sensitivity to an outlier or something like this that shows up in the bootstrapping and doesn't show up in the linear model. But my point here is that these estimates are pretty close. The estimates and the standard errors are about what they should be if the assumptions are true. So if your assumptions are true, you can do the usual linear model stuff, but you can also do the bootstrap, and it sort of works reasonably well in both cases. So that's pretty great. And I'm going to knit this, and then we're going to do one last check, one last sort of look at things. It's taken a minute because I'm doing a bunch of bootstrapping this time. Okay. What did we do? We bootstrapped and analyze results. God, that's so exciting. All right, so the last thing that I'm going to do is revisit a data set, revisit NYC Airbnb. This is one of my favorites. All right, so what we saw previously, let me see if I can actually just get the code that we used in cross-validation. Did we do NYC Airbnb in cross-validation? No, we did that in linear models? Yeah. All right, so I'm gonna copy this code for importing the data set. So I've got the NYC Airbnb data set. I'm taking stars, review scores, location, renaming borough, getting rid of the U in neighborhood, and filtering out Staten Island. Again, apologies to Staten Island. There's just not enough data there to do what we need to. So that's the data that I'm going to need. Oh, I need to load library P8105 data sets first. Now let me try to load this. And one of the things that we looked at in linear models was to take the NYC Airbnb data set and do a plot of stars on the x-axis, and the y-axis is price, and let's just sort of do geom point. So what we get out of this is, it looks like there's probably some relationship between stars and price, but there's also pretty clearly some non-constant variance here, right? This is exactly the kind of thing where if you just did a linear model and you took a look at the results, you would say like, well, I'm getting estimates and I'm getting standard errors, but the standard errors are computed under a framework that just isn't true for this data set. And so what would be nice is if we were able to do an analysis here that gave us the standard errors that are actually sort of the right thing to have. And I guess I'm going to focus even a little bit more closely in. I'm just going to look at Manhattan, both to keep the data set slightly more manageable and because Manhattan was one of the ones that really did have an awful lot of these outliers. So, gosh, is there a way that we can do this? So let me just start out. I'm going to do NYC Airbnb, and let's filter borough equals Manhattan. I need a double equals here. And I get price and stars. It looks like there are a lot of them that, the stars aren't there. So let's drop in on stars and see what my data set actually is. All right, so here we go. And that's, let me just take a quick check that this works. Okay, so again, I've got clearly non-constant variance in the relationship between stars and price, and I've got a few outliers up here. So after I drop in A on stars, what I would like to do to get the standard error for the linear model here is to bootstrap, take a sample with replacement, fit a regression of price against stars, and save the estimated intercept and slope each time. And so that's what I'm going to do. And I'm gonna start here. I'm gonna copy again. I've done some coding once, and so let me just sort of walk through and how this works. So I'm gonna drop in A stars. I'm gonna generate 1,000 Bootstrap samples, and I'm gonna fit a model to each of those Bootstrap samples, where the model I need to fit is price against stars. And then I'm gonna map the results, strap number results, group by, term, mean estimate, standard deviation. This all, I'm gonna cross my fingers. Actually, instead of crossing my fingers and just letting it go, I'm gonna do this 10 times rather than 1,000 times, just to make sure that it seems like things work. Okay, great. Now let me do this 1,000 times. It's gonna take a couple more minutes. I guess while that's running, I'm gonna start out like, let's compare this to LM. All right, so I get an estimated intercept of -34, stars is 43, standard errors of each of those under repeated sampling generated by the Bootstrap are 32 and 6.49. And now I'm just gonna do here, same data set, and I'm gonna do a linear model of price against stars with this data set. And I need to, of course, tidy up the results. And what I get here is, in comparison, I guess I've got something in the middle. So here, the stars, the model-based, what linear, the LM thing tells me, assuming constant variance, is that this standard error should be about 4.7, and what we got under the Bootstrap was about 6.5. So it's quite a bit higher under the Bootstrap than it is under the sort of framework that assumes constant variance. And that's, again, that's roughly what you would expect. If I've got high residual variance over here and I've got some outliers, well, then what I should have is, a little bit more variability in the slope. It's a little bit harder to know exactly where that line is supposed to lie if I do have this non-constant variance. And so that's pretty great. I'm getting here the results that come out of this. And I don't think I'm going to, we could draw, maybe we will. What if I took up to here? This is the sort of thing, it probably makes sense. Let's do Airbnb boot results is everything up to this point. And then I'm gonna say if I took that and here. So the reason that I'm doing this is so that once I get to this point, I don't have to keep rerunning my Bootstrap sample every time. I've decided right now I want to look at some plots too. So it's taken a minute. And if I take a look here, again, I'm getting slightly different things because I have slightly different Bootstrap samples, but that's fine. And now if I take this and let's do that same plot we had done before, let's filter term is equal to stars and do ggplot. On the x-axis is estimate and do geom density. What I'm left with, so this is another thing that's really nice about the Bootstrap, right? Again, assuming constant variance, assuming all of this stuff, you would think that this distribution would be like this nice, neat little normal distribution. And it turns out it's not. It turns out that there's like some pretty clear skewness. There's a little bit more stuff going on over here than there is over here. And my guess is that what happens in general is you get fairly often some of these really high values, and that sort of pulls your estimate up a lot. But every now and then you get a Bootstrap sample that doesn't have any of these particularly large outliers, and you're left with occasionally some estimates that are lower than you would expect. So the other sort of benefit here is that you can get these estimates, you can get this uncertainty, you can get the distribution of your estimates under repeated sampling without having to assume that this follows a normal distribution. You're actually getting what this distribution looks like under repeated sampling, and that's pretty fantastic. So I'm not going to construct confidence intervals. You could use the same code to get a confidence interval for your intercept and slope here, and I'm also not going to say necessarily that this is the right way to analyze this data set. It is entirely possible that you would look at this and say, I want to restrict to rentals that have, a max price less than $1,000 and see maybe, you would still get non-constant variance, but maybe less sensitive to outliers. Some folks might be interested in doing transformations on this. I don't love doing a transformation on the outcome, but some people might. I guess the reason that I don't love doing that is that then I'm looking at, a linear regression of log price on stars, and I don't really know how to interpret a 1-unit increase in stars and the effect that that has on log price. It's hard, you're shifting, now you've got something that's a little bit harder to interpret. So again, I'm not saying necessarily that this is the right analysis, but I am saying that this is a reasonable analysis, and if you wanted to fit a regression here, you would want to get the right estimates and variances of those estimates, and this is how you would do it. So again, lots of stuff going on in this collection of videos. I really appreciate you sticking with it. I feel like for me, taking a step back, this is mind-boggling that what we're able to do in the space of an hour or so is bootstrap, and then bootstrap a different data set, and bootstrap a different data set, and write it in code that, again, is a little bit complicated, at least at first. It's hard, I think a lot of this is harder conceptually once you sort of get used to mapping. Understanding why you would do the bootstrap is difficult. Understanding list columns and mapping is also a challenge. We've been doing it for a few videos now, but it's still, none of this is easy, but I think it's really fantastic that we're able to do this kind of a thing, to do bootstrapping, to do cross-validation, and have those in our toolbox. So thank you very much for sticking with it through these lectures, and that's all I have for now. Thanks.